a body moving in an anti-clockwise fashion, then d theta will be given by right hand rule. So, and d theta will be perpendicular and out of the board. If it is moving clockwise, then again you take your fingers should be able to rotate clockwise, the thumb gives the direction of the vector. So in this case, the vector is into the board. So direction of d theta vector, omega vector and alpha vector is along the axis of rotation, and the direction of these vectors is given by right hand rule. Never ever think that the direction of these vectors is along the direction of motion. It is in the direction of the axis of rotation, and the direction is given by right hand rule. If a rigid body is in pure rotation about any axis, all particles of the body must have the same angular displacement in a given time, same angular velocity and same angular acceleration, because all the particles are locked together. Suppose this fan is in pure rotation, all the blades of the fan must move through a certain angle in a certain time, otherwise something is wrong. Okay, we should run away from here. So basically all the particles of a rigid body in pure rotation must have the same angular displacement, same angular velocity and same angular acceleration, because the particles are locked together. Now let us try to relate the linear and rotational variables. If this is angle theta and the length of this arc is s, radius is r, then theta in radians is s upon r. Whatever be the radius, if you draw an arc, s upon r will be constant for this particular theta, and that is what is theta in radians. So theta in radians is s upon r. So s becomes r theta. If you differentiate this equation with respect to time, you will get the equation v equal to r omega. In vector form, this equation is v vector equal to omega cross r. Again, if you differentiate this equation with respect to time, we will get a equal to r alpha. This is actually the tangential acceleration. Tangential acceleration is equal to r alpha. In vector form, this at vector will be alpha cross r. So s equal to r theta, v equal to r omega, a equal to r alpha. Now we have learned 7 equations of motion in translation motion. This is for translation motion. Equations of motion with constant acceleration a. In the same way, we will have equations of motion for rotational motion. So equation of motion with constant angular acceleration alpha. These equations have been learning since your childhood. V equal to u plus at, s equal to ut plus half at square, v square equal to u square plus 2as. Some more equations we discussed. S equal to Vt minus half At square. S is equal to U plus V by 2 into T, and the distance travelled in the nth second is equal to U plus A by 2, 2n minus 1. Now all these equations will have a rotational equivalent. In rotational motion, V becomes omega, U becomes omega naught, A becomes alpha, time remains T. So the first equation is omega equal to omega naught plus alpha T. Again, in rotational motion, S will become theta, U will become omega naught, A will become alpha. So next equation that we get is theta equal to omega naught T plus half alpha T square. Again, V becomes omega, so omega square equal to omega naught square plus 2 alpha theta. So the next equation is omega square equal to omega naught square plus 2 alpha theta. Similarly, this equation will become theta equal to omega t minus half alpha t square. So theta is equal to omega t minus half alpha t square. This equation becomes theta equal to omega naught plus omega by 2 into t. The equation is theta equal to omega naught plus omega by 2 into t. This equation can be written as theta n equal to omega naught plus alpha by 2 to n minus 1. Most of the equations that are going to develop in rotational motion are just rotational analogs to the equations that we have learnt in translational motion. So it is very easy to get these equations. V becomes omega, U becomes omega naught, A becomes alpha, T remains T, S becomes theta. Right? Very simple. Now let me ask you a simple question. This is a rotating table. So this is the top view and this is a rotating table. Rotating about this axis. Now, if you look at this point A that is on the circumference, and this is another point on the circumference, point B. Point C is a distance of r by 2. R is the radius of this rotating table. So this table is rotating with some angular velocity. Now let me ask you the first question. Is omega at A equal to omega at B? Okay, both will be same, right? So omega at A is equal to omega at B. Is omega A vector equal to omega B vector? Yes or no? He is saying they are not same. Are they same? What about omega at A and omega at C? Is omega at A equal to omega at C? And what about this vector relationship? Omega at A vector equal to omega at C vector. Are they same or they are different? Which of the following four is correct? Omega at A and omega at B will be same, right? In magnitude. Everyone agrees with that? The vectors will also be same, because at both the places omega is dependent on the direction of the angular velocity, and it will be perpendicular to the plane and out of the board. Omega is not in this direction. Omega is perpendicular to the plane and out of the board. So direction of omega at A and the omega at B will be exactly same. So this is also correct.